Now that we have the ratio comparison test, this is now going to be our go-to test. So we have this series. It's got n squared and log n to the power n. So we're going to set this up as a ratio comparison. So limit as n goes to infinity. The ratio that we're going to use is the consecutive ratios. So in the numerator, I'm going to do the n plus 1 squared over log of n plus 1, and that term is going to be to the power n. And then the denominator is going to be n squared over log n to the power n. Okay, so I'm going to group some of these terms. So it looks like I could probably group those n terms. So when I write this out, this is going to be equal to limit as n approaches infinity, and grouping together the n terms, I'm going to end up with n plus 1 over n, and that's going to be all squared. Okay, it looks like that's going to be equal to 1 squared. And then I'm going to group the other terms, the log terms. I forgot an n plus 1 up here, so that's going to be an n plus 1. And when I group those together, it's going to look like this. The log n to the n is going to be in the numerator. We also have power, so this is going to be to the power n. And we're going to end up with the log of n plus 1 all to the power n plus 1. That's going to be in the denominator. Okay, so we can simplify some of this. This is going to look like the limit as n approaches infinity. That part there is going to end up being 1 squared. This portion here, when we simplify it, well, it looks like we're going to have something that looks like this. So I'm going to split this up a little bit, and we're going to end up with log n over log n plus 1 to the power of n. Now we have that extra plus 1 here, so I've got to account for that, and that's going to be 1 over log of n plus 1. That's that extra plus 1 in there. Okay, so evaluating this limit then, this becomes 1 squared, which is 1. This is log n over log n plus 1, so that's log infinity over log infinity. Well, that's the same infinity, so we're just going to say that's equal to 1 to the power of n. Okay, so that's also going to end up being equal to 1. And so all that we're left with is log of 1 over n plus 1 as n goes to infinity. That becomes 1 over infinity. That's 0. So in this case, that is the limit is equal to 1. So that ratio goes to, it's equal to 0. So that ratio goes to 0. Okay, if the ratio goes to 0, I know that's less than 1 because I'm looking for the ratio test is less than 1. It converges. That's what I really want. I want it to converge. There's less than 1. Therefore, I now make my conclusion. This is a convergent series. Okay, so this series it does converge. So this last one is a little bit different, and now we're mixing x's with our n's. So this is now starting to get into these polynomial series. So we have our power series, which we're going to mix in with our n series. Okay, well, let's see if this whole thing converges by setting it up as a ratio test, because again, that's kind of our go-to test. Now, this is, if you recall, these are series that represent functions. So we're going to set this up as a ratio. It's a limit as n approaches infinity. And I'm going to end up with, in the numerator, I'm going to end up with x to the power n plus 1 over n plus 1 factorial. That's my numerator. In the denominator, I'm just going to end up with x to the power n over n factorial. Okay, so I'm going to group some of these terms. I'm going to group the factorial terms, limit as n approaches infinity. This becomes n factorial over n plus 1 factorial, which we're going to simplify that expression. There's also these x terms, which I'm going to separate out. So I end up with x to the n plus 1 over x to the n. Okay, so I can simplify this before I apply the limit. Evaluate the limit. So limit as n approaches infinity. That's going to have an extra n plus 1 in the denominator. So the n factorial cancels out. And we're just left with an x plus 1 in the denominator. Sorry, n plus 1 in the denominator. The x's here will cancel out, so we have an extra x in the numerator, so this is just times x. And then I'm going to let n approach infinity and evaluate this limit. This becomes 0 times, well, x is not part of this, so it's going to be 0 times x. Now, our ratio test is going to be independent of that x, because 0 times anything is 0. So at this point, this is equal to 0, which is less than 1. We can make the conclusion. Therefore, this is a convergent series. Okay, well, there's some implications to this now. It's a convergent series, so this is what we've always wanted. We want these converging series. But this series also is a polynomial series that represents a function. And this function has x's that we can plug into it. Now, what about this x? How can this x affect this series? In this case, it doesn't affect it because of that 0 that we generated here. That 0 makes that x irrelevant. So regardless of what that x is, this series will work. Or in other words, this series can represent that function. And the domain of that function is going to be valid for x is all real numbers. So this then now represents the domain of that polynomial series function, and it works for whatever x's that we want it to work for. Now, we've seen some series, some power series where we had limited domains, and that can still happen. But in this particular case, this series, whatever it is, whatever it represents, is good for all real values of x now, because it passes our ratio test irregardless of what x is. So to summarize then, these tests are basically a comparison. We've done some new tests here. We came up with the ratio, the nth root test. Okay, our nth root test is what a new one that we looked at today. The ratio test, which is our go-to one. This is our most important one. This is one we want to use most of the time. Those tests are now a complement to our informal tests. Okay, and we can start using these tests, in particular the ratio test, to help us with these polynomial series. Because remember, that's our end goal, is to generate and evaluate these polynomial series. And we can do this best with these ratio tests, because we still need to test for convergence.